It's my pleasure to introduce Dr. Jack Birkin. He's a postdoc at Texas A&M under Professor Justin Spilker, who was here last year. Before going to Texas A&M, Jack did his undergrad and doctoral thesis at Durham, UK, under Professor Ian Smale and Swinbank. And he was kind of in our rival group.
I was expecting to hear booze.
Yeah, I don't think many people know that, so but it's fine. Maybe David knows. But yeah, he's been fun to work with for the past 3-4 years now.
Three
Yeah,
years.
yeah. He's part of he's part of the templates group as well as the SPT-SMG group, which we will talk about a little bit today. So I'll give it to Jack.
Thanks, Kedar. Yeah, thank you. Thank you to Joaquin as well for inviting me, and thank you to all the people I've spoken with so far for chatting and sharing knowledge with me. I feel like I've learned quite a lot today already. It's really nice to be back here. It's been two years, I think, 2.5 years since I was here, and I've seen some people that I haven't seen for a while, which is great. This talk is something fairly new for me. I'm not actually going to present a paper. This is actually going to be my last talk in astronomy because my postdoc is ending in about a week's time, and I'm planning to leave the field after that. So I'm going to be talking about a tool that I built to hopefully help my collaborators once I'm out of the field. So my research interest, just to go into the background, my research interest is, and it always has been, sub-millimeter galaxies, or SMGs for short. Sometimes we just call these dusty star-forming galaxies erroneously, but I probably use those two terms interchangeably today. So I'd like to start by addressing the question of why are these sources interesting? What are they, and what is special about them? So even as our view of the universe, even as we go out to higher and higher redshifts, as we are right now with the JWST and other telescopes, sub-millimeter galaxies are still some of the most fascinating systems out there. Usually, we observe them in some kind of a starburst phase, so they're forming stars very, very rapidly, and that means that they're very dusty. So they're enshrouded by dust, and as a result, all the light that is coming from stars, particularly young stars within these galaxies, that light is being absorbed, being re-emitted in the infrared. So the dust is being heated, and then it's re-emitting that light at longer wavelengths. So they're typically not optically bright, they're actually infrared bright. So the majority of progress studying these galaxies has been driven by millimeter wave telescopes, things like ALMA, and as I'll talk about today, SPT. So the figures I'm showing here are kind of a broad evolution in the field, that going from the blobs at the top down towards some of the JWST images that we have right now at the bottom. Really, our understanding of these sources has evolved quite rapidly in the last few decades. And the samples of these galaxies is probably a couple of thousand that we've detected in total, but most of them have not been studied in any great detail. So there's a lot of room for progress in this field. And in general, the ones that get studied the most are the more extreme ones, which is kind of a double-edged sword because you study the extreme sources and you don't get a representative view of the whole population, but you learn something about what makes the extreme ones more extreme. And we normally, the reason we call them sub-millimeter is that we select them at around about 850 microns, which we benefit from a neat trick where if you look at the 850 micron observed point in the top plot, the going from blue to red, you're going to sources at higher redshift. And so because of the way that the redshifting works, you actually move up the tail of the dust distribution, of the dust SED. And so sources actually become brighter somewhat as you go out to higher redshift. And that roughly cancels out cosmological dimming. And so really what that means is that we can find these sources and observe them over quite a large volume, quite a large redshift range. And that's one of the things that makes them an interesting population to study. So if you look at the bottom plot, one of the purple lines, I think is 850, and that line is roughly flat between redshift 1 and 7 or 8 or something like that. So in theory, in that redshift range, the sources should intrinsically be, or you should observe them with fairly similar fluxes. So what science questions are still open in this field? So things like why are these sources so extreme? What exactly is it that makes them, that triggers their star formation? It's thought that there is a connection between these sources and the local quiescent galaxies. So they should, in theory, go through some quenching where the rapid star formation stops, and then we end up with something like the type of galaxy that we see locally. What about energetic black holes, AGN? Do we see these in most of these galaxies, if any? Things like how representative are these galaxies of the high redshift population? Feedback, and then many other questions. I myself have been particularly interested in, for example, the top one. I really want to know why these galaxies are so highly star forming. But I've also, in recent years, been more interested in AGN within these sources. So yeah, I've been working on these guys for quite a while, almost 8 years, I think. I started my PhD in 2018, late 2018. And I've used a variety of telescopes. I've done research with ALMA in the submillimeter, and also with some optical telescopes like JWST. I wrote my thesis on these sources back in the UK, as Kedar mentioned. Mostly I was focused on SMGs that are not lensed, which is kind of a difference with what I'm doing now, working with SPT, where most of the galaxies are lensed. And I moved to Texas a few years ago to do a postdoc. So I've been part of the SPT collaboration ever since. So yeah, I've spent quite a lot of my life now at this point working on these types of galaxy. As I mentioned earlier, I'm going to be leaving the field fairly soon. And I didn't really have enough time to start a whole new project, write a whole paper. And so what I'm going to talk about today, I wanted to kind of make good use of my time and create a tool for my collaborators, because I really enjoy the coding part of my job. I'm trying to make a transition more towards data engineering. And so I was trying to brush up on my coding skills. And so I wanted to make a tool for the new generation of SPT data, because I think that's bringing new challenges in terms of how we inspect the data and how we select targets for follow-up. So at the forefront of all of this is the South Pole Telescope, which has been one of the most important telescopes as far as dusty galaxies go. It's located obviously at the South Pole, about 10,000 feet altitude, I believe. I can get really, really cold there. I can get as low as minus 100 Fahrenheit, I read recently. And conditions there are really, really great. It's very dry. The atmosphere is very, very stable. And for observing at millimeter wavelengths where water vapor emits in quite a lot, you want conditions where you can get around that if you want to observe things that are faint. And whereas we have interferometers like ALMA, which can do really detailed high-resolution studies, SPT is great at doing big surveys. And so over the last 20 years, it's surveyed a really, really large part of the southern sky and found a lot of really interesting SMGs, particularly ones that are, as I mentioned earlier, gravitationally lensed. And because those sources tend to be rare, and if you can survey a really large area of the sky, you can find a lot of sources that are lensed. And what that actually means is that the lensing boosts your the sources are magnified, and you can observe them in more detail because you're effectively boosting your spatial resolution. And just to note that this is only a part of the SPT research output. Yeah.
How heavy is the telescope? It looks like it's lensing the sun. What is this optical effect here?
That's a good
that photo.
That's a good question.
That is a sundog. So the ice crystal. The sun is right behind the telescope, okay. And so it's kind of like a rainbow where light's getting refracted by ice crystals. And so it's just how they took that photo. You see the shadow. So the sun's right behind the telescope being blocked, and then the sundog. So usually you put your hand up and squint. But like,
So if you zoom in, you probably see a little rainbow on that ring.
Yeah, you can see it on the kind of the edge a little bit.
Oh, that's cool.
Yeah. Yeah, so a really unique place to have a telescope, and it would have been really cool to actually have gone out there, but I'm not really probably as involved as I need to be to get that privilege. But yeah, it's such a cool thing that we have a telescope there. This is just to kind of highlight what the lensing does. You have a foreground galaxy, and because of the way that space-time is bent around the foreground galaxy, you have the light from the background galaxy is being magnified, and then you see something kind of like the background there. In this case, it's a ring because of the way that the light is being deflected around that foreground galaxy. And so that effectively boosts your sensitivity and your angular resolution, and so you can study galaxies on much smaller spatial scales than you would normally be able to. So there's kind of a trade-off with this, because when I was in grad school, we tended to ignore the lens galaxies because they're actually quite hard. You really have to be able to take that observed image and reverse engineer what the galaxy looks like in the source plane, and that introduces complications. But if you have the expertise to do that, then you can really learn a lot from lensing. So this plot kind of shows where we're at right now. These are 8 of the probably the most prominent SPT submillimeter galaxies that we have that we're observing right now. These images are from JWST NearCam, and I think the ones in the bottom corners are MIRI, so those are mid-infrared. I myself did some work on the 2 in the top right-hand corner, which were part of the templates program that Kedar mentioned earlier. So one of the things that we're finding with these galaxies is that they all seem to have small companions, small galaxies that are nearby and probably interacting. And that itself would induce star formation. So that kind of goes back to one of the questions that I addressed earlier about what triggers the rapid star formation in these sources. SPT-311 in the bottom right-hand corner, that's one of the crowning achievements probably of the survey in terms of SMGs. It's the highest redshift source from the survey. I think it's still the highest redshift SMG. It's kind of a mishmash of various clumps, which some of them are UV bright and some of them are dusty. It's really a really interesting system. And so we're doing quite a lot of stuff with this new data. Just to orient you, the top right is what we saw before. The 2147 is one of the galaxies that I looked at fairly recently, and then this here in the bottom right shows that 0311, the really high redshift source in more detail, and that was work by my boss Justin Spilker. So yeah, there's lots of things that we're doing right now. There's a lot of work going on with these sources. So it's a really good time to be working on this. But so how did we get to this point? I thought I would go and try and educate myself a little bit on this. It's been about 20 years since SPT achieved first light. I believe it was almost 19 years ago to the day, February 16, 2007, I think. Joaquin can correct me if any of this is wrong. And within a few years of that, the first generation of SPT was the SZ survey. And the main science goal, SZ, stands for the Sunyaev-Zeldovich effect, which is a distortion of the cosmic microwave background by high-energy electrons in galaxy clusters. So that was one of the main motivations for this telescope. The SMG stuff is it's not one of the things that first gets mentioned when people talk about this telescope. And so that first survey was a 2,500 square degrees, a really big area of the sky. A few years later, the camera was upgraded so that it could measure polarization and continue to do these really, really big surveys. And then the third generation camera, which is kind of getting to the point of why I'm here, that was installed 2017 and brought really, really large advancements over the previous two. And currently, 3G is operating. It's, I believe, surveyed about 10,000 square degrees of the sky. That's to varying depths. The main survey is about 1,500 square degrees. But this really is the key point. It's why I'm here, because we have a lot of new data from this camera, and we need to start sifting through it. So this is just to say that this was just a pretty picture I wanted to show that I found on the U Chicago website. The new camera has, I think the number of detectors went from 1,500-ish from SPT Pol, the second generation, to about 16,000. So they're over 10 times more detectors, and that means that increased mapping speed, much lower noise, and so we can really start finding. I mean, first of all, it's great for the CMB science and the big goals of the telescope, but for us studying SMGs, we should really be able to find more faint sources, and probably as a result, more distant ones. So this plot shows, just for context, the kind of yellowy region is the 1,500 square degrees, where the main survey area of the 3G instrument. And then more relevant for this talk is the square region in the middle, where we actually, first of all, we have the new data from 3G, and it's co-added together with the previous generation SPT Pol data, but also it's covered by a range of other multi-wavelength data, like Herschel SPIRE, which is here in the shown on the bottom row, and that data covers the kind of far infrared where the dust emission from these sources peaks. And one thing that I think you can kind of see, which is interesting from this, is so if you look at the 95 and 150 gigahertz images up there, compared with the SPIRE data, the resolution is fairly low. So that kind of highlights one of the initial problems with studying these galaxies was you would detect them with millimeter telescopes with really, really big beams, so really, really large PSFs effectively, and you would find the emission, but it would be really hard to then attribute that to any counterpart in any other wavelengths, because you wouldn't be able to really constrain the position very well because of how large the beam is. And so originally this was, I think, the first telescope that discovered the first SMGs. I think the beam was like 15 arc seconds or something like that, so really, really hard to do any kind of science with it. This is another version, essentially, of the same thing, but this one comes from a recent MeerKAT proposal. So MeerKAT is a radio interferometer, which I'm going to talk about a little bit more, but this was from a proposal led by Roger Dean in South Africa. And the reason I like it is because it has this zoom in on the right of the 100 square degree field that I'm most interested in right now. And you can see the moon, which is kind of a nice bit of context. Yeah, so the MeerKAT image you can see there in the bottom right. One thing that I think is interesting to note, again, going back to what I just said, is how many sources there are within that particular small cutout that's circled compared with the SPT cutout, and that highlights one of the challenges of matching sources in different catalogs. So this 100 square degree field is actually a 94 square degree field, I think. Yeah, there's really a lot of data available. Apparently, it's among the cleanest 1% of 100 square degree regions of the sky in terms of emission from the Milky Way, which I didn't know that. But that makes sense as to why it was chosen. And as you can see, the plot in the top right, the filled point, this has really deep data from Spitzer, which is a near-infrared telescope. I won't be talking about that data really today, but just kind of just to highlight what is important about this field. And it's also a really, really big field as well. There's a lot of area there to find sources in. To talk about just a couple of the other facilities that are relevant for this particular analysis. So MeerKAT, as I mentioned earlier, this is a radio interferometer which is located in the northern Cape of South Africa. It has 64 dishes and observes at around about a gigahertz. It's actually the precursor to the square kilometer array, which is an interferometer which is going to span both South Africa and Australia once it's complete, and it'll have a total collecting area of 1 square kilometer, which is really, really big. And one of the good things about having data from this telescope, because it's an interferometer, it has very, very high spatial resolution compared to the SPT data. And that allows us to, that gives us an anchor to find the counterparts. So I mentioned that we have really, really big blobs essentially from SPT, and then we want to attribute them to a radio galaxy. We can use the data from MeerKAT to do that. And it also allows us to do a bunch of other useful things in terms of constraining star formation and also AGN and lots of other things. So we actually also just had a big program approved with MeerKAT to observe. I don't remember whether it's all of or most of that 1500 square degree field, but that's an 800-hour program. Obviously, we already have 100 square degrees observed, but really, really huge, a lot of time approved, which is great because right now it feels really difficult to get time on telescopes. So this was good news, and there's a good variety of goals that we can try and work towards from the data that we have with this telescope. And on the higher energy side of things, we have Herschel, which was a space telescope, and the SPIRE camera, which covers 250 to 500 microns. If I had showed you the plot from right at the start of the talk, you would see that that's around about where the dust, the dust SED peaks. And that means that it's really useful for identifying and characterizing submillimeter galaxies. Herschel was decommissioned over 10 years ago, but it's still, I mean, we still use this data a lot, so it's still very useful. And as I say, the observations, they sample that peak of the dust SED, and that makes them really useful for finding and selecting SMGs. So moving forward to right now and right here, so just talking about what the motivation was from my end on doing this project. So SPT-3G, as I said earlier, it's been going for quite a while, but really the SMG collaboration, we're only just starting to work through the data that is coming in. And so we spent a lot of time planning and trying to figure out what science we want to be doing, and what proposals we want to write, what papers we want to write. So one of the best places for us to start really was to look for the most remarkable systems. Let's just see if we can find which ones that really stand out. It's kind of a low-hanging fruit place to start. So remember, we had SPT-0311, which is right here at redshift 7. Can we find something further away, something even more interesting than that? And that would be really cool. I think that would be a great place to start with this new survey. And as I said earlier, because of the negative K correction that we have with these sources, we should actually be able to detect SMGs out to even higher redshifts. This plot from a paper by Cassie, who was here a few years ago. I don't remember at what point she left here, but she was here before. Shows that the prediction that we should be able to find sources out to redshift 8 at least. So these are SMG counts as a function of redshift. And detecting them is one thing, but actually figuring out what redshift they're at is another, because when you only have a few bands of kind of narrow band data, it's hard to confirm a redshift without a spectral line. And there are also degeneracies because of dust temperature and color. So sometimes you might see something that looks to be a really high redshift, but actually it's not. And so that's kind of one of the challenges that we deal with. And so yeah, this is just to show that 0311 lives right there in that region at the end. So if there are sources there, then we do want to try and find them and study them. I can stop now. That's all right. We can break. I'll do it after the slide. So in theory, within that full 1500 square degree survey, there should be a few tens of sources out at redshift 7 or 8. Even just within, so the blue line shows that 100 square degree field that I talked about originally. There should be a handful of sources out at redshift 7 or so, and that was kind of the theory that we wanted to test as a starting point from looking at the new data. We've already said that we can probably detect those sources, but establishing the correct redshift is difficult, especially when we only have 3 SPT bands. And so we pull in other data, and one of our kind of theories with this was that the plot on the right is showing you 3 lines. So one is from each of the instruments that I just discussed earlier. And those lines show a theoretical detection limit in far infrared luminosity. So put simply, you should be able to detect anything that is at least as bright as where the line is for a given redshift. So, and that's for each telescope. So with SPT, the line kind of plateaus, and that's because of that K correction. As you go up to higher redshift, you can still detect things fairly well. But with MeerKAT and SPIRE, as you go up to higher redshift, those things are going to start to disappear in your data. And so the idea that we had was we could see what sources show up in SPT but don't show up in MeerKAT and SPIRE. And so that was, for Kedar and Cassie and I, that was the initial idea that we had for a proposal that we wrote last year. I can pause right. Yeah, so in theory, we should be able to find these high redshift sources if they exist, and they should exist, based on a veto with the 2 telescopes that are not SPT, the MeerKAT and SPIRE data. And then I guess the idea is that we can follow up with like ALMA and other telescopes.
There's a question.
Oh, sorry.
Why SPT has a peak around around 1? Like there is a peak for SPT.
On the previous slide?
Yeah. Why
There?
is this peak?
So that's just because, so essentially all you're doing here is you're taking the SED of one of these galaxies and just moving it and just redshifting it. And so you start, I'm trying to get my head in the right picture for this. Yeah, I can go back to this. That's a good idea.
That's what we're least sensitive.
There's the second plot. Yeah.
Yeah, so the one, as you go to really high redshift, like you're moving up, the 850 micro or the 1 millimeter point is moving up the SED, but like that initial increase in peak is like the point where you're moving down. Like, so it's just kind of a case of like you start at a certain point on the SED and then you move along it. And so initially you're kind of moving up, or initially you're moving down and then you're moving back up. That probably didn't explain that very well, but it's literally just where you are on that SED, and then also like combined with the cosmological dimming as well.
Yeah, so the first thing is 1 over r squared, the luminosity distance. And then at some point you start, because of the redshifting of the universe, you start going up the SED. So that's the top part. So the galaxy, the part that's brighter gets redshifted near it. That counteracts the dimming due to luminosity distance. So the flux, the power you receive, is shown on the bottom. So it goes down as you move this thing away. Bottoms out about redshift 1. So it's not a peak, it's a trough. It's the dimmest
Yeah.
source of luminosity. And then it increases in there. So that other plot he was showing was the inverse of this bottom plot. So flux density limit.
Yeah, so this is saying that this is like your sensitivity, whereas the other plot is you're saying things have to be at least this bright for you to detect them. So for ALMA cycle 12, which was last April, last May, something like that, Kedar, Cassie, and I, we worked together on a proposal to exploit this. And as I say, at this point, most of the data hadn't really been thoroughly explored. This was kind of, at least from my point of view, this was kind of first steps into actually looking at the 3G data. And so I started working on a tool that it was mostly for myself, I guess, but also kind of somewhat something I wanted to share. A tool that would allow us to interactively look at all the data and leave our own comments in a collaborative way. I felt that there's sometimes a lot of wasted effort where people make their own plots and then they'll show them on a call or something, but after that, they kind of get forgotten about. And so I wanted to make a tool like a centralized place where people could look at the data that I was looking at, and then they could leave their own comments, and people could do things asynchronously, so without having to all be on a call at the same time. And so between Kadar and myself, I think we use this tool a little bit, but not much. It's pretty minimal version. But that proposal ended up being successful, which was really good because, as I said earlier, it's quite tough to get time on telescopes right now, particularly ALMA. ALMA is a really tough nut to crack because there's just so many people who want ALMA time. And so we got that data, which is really cool. And as I alluded to before, we spent a lot of time making various cuts to this. So we would take the 3G catalog and we would say, we want to find the sources that are not detected in this sample but are detected in this one. And so that itself is pretty trivial, but really it's really important to actually look at the images. Like you can make a cut to a catalog and then trust that, but it's so important to actually look at the images and see if everything makes sense, because things can get lost, things can go wrong. And it was really hammered into me by my grad school advisor that you have to look at the data. Don't just assume that your pipeline is going to work properly. And we've got a lot of great tools in astronomy, but I think that in some places there is a lot of room to develop things that can save time and energy down the line. So that was kind of what I was getting at. So I made this tool, application, whatever you want to call it. I spent some time fleshing out what I started working on when doing the proposal. So all it is, it's a Python. It's a pretty much entirely Python interactive application. Has an interactive interface which is built with Dash. So Dash is a Python framework which allows you to work in HTML and CSS, so you can effectively build out a web page. And the idea was that I wanted our collaborators to be able to easily find all the sources that were going to be relevant to them, search for ones that they were looking for, and then look at the images of that galaxy. And then, and I say look at the images and leave notes and in a centralized way that other people can use for proposal planning and also for paper writing. It kind of looks like this. This is the rough interface. So you have a table of the whole. I mean, obviously you can't see all of the sources, but a table with coordinates, fluxes, spectral slopes, things like that, paired with the image on the right. And the users, you can search for a source by name. You can filter out for example, if you're interested in the most distant, the sources with the highest photometric redshifts, you can say, I'm going to select the ones that are at the top, and then I'm going to sort the table. And then you can view on the right where those sources are in the field, which I think can be quite a handy thing, because sometimes, for whatever reason, there may be some kind of structure that exists, and there might be some clustered sources that are relevant. And then you can click on any source, and you can filter the table, and then you can go and look at the images. And I think this will be really helpful for my collaborators. So what I'm showing here is in the top left is the MeerKAT data. Along the top is the SPT data, and then the bottom is the SPIRE data. So you can kind of see the native resolution. As I highlighted earlier, that really high source density in the MeerKAT images compared with the SPT, and again, that being one of the challenges that we had to deal with when writing this proposal, and that we'll continue to have to deal with. But I think one of the most helpful things in terms of this tool is that see the dialog box in the bottom corner. People can leave their own comments and save them, and then everyone can view those comments whenever they want. So if there's a call and people say, well, we have these 20 sources we want to look at, people can then go to those sources, find them, look at them, and leave comments. And I think that will really, it's a pretty simple thing, but I think it will enable some more effective collaboration than perhaps we would have had before. I also allowed the ability to show the native resolution and the SPT convolved images. So in this case, all the data is convolved to the same beam size as SPT, which can be handy. So just before I end, I was going to talk a bit about how this just works on a more technical level. I'm relatively new to this stuff, so I actually learned quite a lot. And I don't think that this is particularly complicated. I think that I would encourage people to go out and try and do stuff like this yourselves, because I think that you can learn a lot, and you can also improve the way that you do things. So it's built around, as I said, Dash, which kind of connects various frameworks. The first is React, which is a JavaScript framework, and that handles all the user interface, the browser, the user interactions. You also have Plotly Dash. Dash is the thing which connects the Python code and the backend with the user interface in the browser. And then you have Flask, which is a Python framework that runs the server and executes all of the callbacks that are returned by the Python code and updates the browser. So pretty straightforward thing. This didn't take a lot of work. It took more work to tune it than anything, but the actual concept is fairly simple. It's a modular Python structure. I just put up the file tree on the right just to kind of indicate that there's not a lot going on here. All of the images and the cutouts are stored on disk. They're stored with all this. So yeah, pretty straightforward in general. And yeah, it didn't really take that much work, but I think the payoff is going to be pretty good for the collaboration. Just to kind of highlight that again, you start with a browser. You have things like buttons and drop-downs and tables. That's all handled by the React part of the code, which is the JavaScript part. That handles all your clicks and interactions. That's passed by Dash to the backend, to the Python code. It handles sending requests to the servers. Then you have Flask, which handles the Python app logic, the layout and the state of the app. And then the stuff on the back was mostly the kind of thing that I've been writing before in Python, just like sorting tables, loading tables, generating images, loading data, pretty simple stuff. And then that logic just passes it back to the browser and updates it. So really a pretty straightforward thing. Didn't take that much work, and I think, as I say, I think this is going to be quite worth it. In terms of what we're doing next with this, I've been talking a lot with Andrew today and Kedar and other people and Joaquin, and we're working on transferring this to be hosted at NCSA right now. I think there are some improvements to be made. I think if I had more time, I would have added a bunch more stuff, but I'm sure that my collaborators can add some of these things if they want to. And also, I guess if anybody has any suggestions based on the things that they've seen today, that's very welcome. I'm very open to that. But yeah, that's about it, actually. So thank you for listening, and I hope you enjoyed it. I don't expect you to do anything. In terms of what do I want them to use it for, or in terms of to develop the? Well, I guess I think that the first obvious thing to me is that we talked about this is purely the 100 square degree fields. Eventually, SPT, we're going to get the data from the full 1500 square degree field, and so it's going to need to be expanded to include the full survey area, potentially. There's also IRAC data and WISE data and Euclid, I don't know as well, maybe. So there's other data that will need to be added. If it's going to be useful, then there's that for sure. I think the technical stuff probably is more for Andrew to deal with, but I think he can probably set this up in a way that is probably more efficient than I've built it myself. But yeah, I think those are the main things really. Yeah.
Yeah, one of the aspects of this that I think is interesting is the social collaborative element. I know it's simple. It's like just jot a note down to annotate something. But a lot of times those collaborative tools and services are simple, but they enable a lot of like efficiencies.
Yeah.
You know.
Yeah.
And I guess that makes me curious about what in this relatively small subfield, I guess, this collaboration. Like, what are your collaborative tools and services? Is it just chat with each other by email and Slack, see each other at conferences? Do you have, what are the technical ways that you guys communicate?
Currently, it's just chat on Slack and email, and once a week, common set of data storage.
So you have the only unified place to store data or documents or anything is a traditional cluster server?
Yeah.
Let's see. Gotcha.
Yeah.
And what? Google Drive. So you use Google Drive for documents?
Yeah, some of them.
As in, people just write a document, some rando owns it, and then shares a public link? But not I guess what I'm getting at, is it a collaboration-owned Google account? Okay. Cool.
It's walk-in and me posting folders.
Gotcha. Oh, I see. So it's like Joaquin retires and then that vaporizes. Okay, just making. No. This sounds. This is not a joke. Not just because we want Joaquin to leave, but because. Did I say that out loud? I didn't mean that. Yeah. Well, the thing is, so recently in the Muses project, a physicist leader in this field, he just abruptly left physics entirely. As soon as he left his university, all of his web infrastructure was taken offline, and he had been using that as basically the DOI for all their data sets. And so our tooling started breaking. I was like, what? Why can't it access this? You know. So I mean, I'm bringing this up partially because this is an issue that I feel like these subfields need to kind of grow up about their collaborative infrastructure.
Yeah, and I was very aware of
what
that.
you're using.
Yeah, I was very aware of that when I was doing this because I think I'm happy to be kind of hanging around long enough to like help with the handing over of this. But I know that some people would probably just, when they're done, and they're not interested in sticking around to work on things if they're not getting paid. So I'm like, that was something I was cognizant of when I was, and even just with my general work, like making sure that all my code is available, and because I still get people asking me for data from papers that I wrote years ago, and it's like there's got to be a better way to deal with it all, you know. And we're pretty, I guess in the grand scheme of things, we're a fairly small collaboration, our subset of SPT, but that doesn't mean that we can't like find some. We don't necessarily need the most scalable solutions, but we can still find things to make things more effective. Yeah.
So when you are looking at the thumbnails, and what kind of things are you looking for to comment on that are interesting about the images, the cutouts, and the
So
thumbnails?
I guess one of a good example that comes to mind. So when we were writing the proposal, one of the things that Kedar and I worked on was matching the SPT catalog with the MeerKAT catalog. So the radio data up in the top left with the SPT data. And we were using some software to do like a probabilistic catalog matching. So we would go in and say like, you would have your SPT catalog, and each source would have a position and a positional uncertainty, and the same for MeerKAT, and we would match them. And one of the things that I found this really useful for was checking the output of that code to make sure that I was getting probability matches that made sense. So if I like looked, and in this case, you know, this one you can see there's a bright source in MeerKAT within the contours of SPT. So in that case, it's somewhat likely that there's a match there, but like the code, like the catalog matching code might return like a definite match, but I still would like to go and look at the data and make sure that it actually makes sense, because if I don't know 100% what the code is doing, I would like to visually inspect it and visually make sure that. So that's kind of one example.
Okay, so in that kind of example, it's more of like a note taking on output. Of the
so
code.
I think for me, my thoughts when I was doing this were more like sanity checking things. Mm-hmm. I can imagine that some of my collaborators who are a bit more forward thinking would probably be looking more at structures in the various bands, but when I designed this, it was more about testing things and making sure, if simple things like, am I looking at the same coordinates? So I'm actually looking at the same, in the same place. So a variety of things.
Yeah, I could see some functionality of this being useful for transients when because we look at something and we say this is probably an AGM, but there's no way to quantify it.
Yeah.
Comment that.
Yeah.
Yeah.